Hello everyone, welcome back. Today we will solve problem number 10 in DeepML, which is to calculate a covariance matrix. So in this problem, we're given some vectors, and then we have to come up with a covariance matrix for these vectors. Now, as it's tradition, what I'm going to do is first talk a little bit about the covariance matrix and why do we care. Then I'm going to talk a little bit about the official solution, which is kind of coding this up from scratch. And then I'm going to talk about the Numpy solution, which is a one-liner, and it's what you will most likely than not use in your personal projects. So without any further ado, let's dive right into it. So if you've worked with the dataset, you most likely than not are familiar with variance and expected value. And if you're not very familiar with covariance, don't worry. We're just going to see that it's kind of a generalization of the variance. So let's start with one of the most typical examples. Let's say we have a data set that has information about houses. So in this data set, each row corresponds to a specific house, and each column corresponds to a variable associated with the house. So for example, we would have number of bedrooms, and then we could have another column, which is the number of bathrooms. And just for completeness sake, let's say we have the price, so on and so forth. So we can do a lot of things with this data set, but let's first think about what we could do if we're trying to understand the data set itself. So one of the first things you would do is you would look at each column independently and try to say stuff about it. So for example, if you're looking only at the column of the number of bedrooms, you could come up with a question such as, what is the mean number of bedrooms, right? And you can calculate the sample mean, which is just like a specific case of the expected value. So if X were to be the number of bedrooms, the expected value of X would be what this mean represents. And another question that you could ask is how dispersed are the values? And for that, we usually use the variance. And in case you forgot, what the variance is telling you is expected value of X minus expected value of X, all of that squared. So in plain English, what that is telling you is, well, how dispersed, or rather how far apart are the values within my data set with respect to the mean. And the good thing about the variance, or rather one of its properties, as we can see here that this thing is squared, is that it's going to be greater or equal than 0. And so if we were to plot this, if we had, let's say, a data set with a very small variance, so in this case, this blue line is going to be a variance that's close to 0, then we would more likely than not see something like this. We would see like a, let's say that the mean is 0. This is not my best drawing, but what I'm trying to say is that the values would tend to be very clustered over there. In contrast, if you were to have a variance that's very big, very large and 0, you would more likely than not see something more like this, more like kind of a line. It's kind of uniform, right? All of the values are very spread out. They're not clustered around the mean. And so you can get an idea of how these things work. So this is a very simple way of understanding this. But this is what happens when you're looking at only one column. So now a natural question would be, well, how are columns related with one another? How are the values of the columns related with one another? So for example, let's say X, again, is the number of bedrooms, and Y is going to be the number of bathrooms. That was a tricky one. So something that would be natural, if you just think about what this data set represents, is that the more bedrooms you have, the more bathrooms you will have as well, right? They should be going hand in hand. And that can be understood using what's called the correlation coefficient, but we're not going to talk about that right now. What we're going to talk about that is the covariance, which is very intrinsically related to the correlation coefficient, but it's going to tell us something a little bit different. So if we were to see how whenever we vary X, we can see a variation on Y, we would calculate what's known as the covariance. And it comes from this formula that we have right here. So it's going to be X minus expected value of X. And that's going to be multiplied with Y minus the expected value of Y. So what this is telling you is, okay, let's multiply how different, for each observation, we're multiplying how different the variable x is to its mean and how different the variable y is to its mean. And so we get this little number right here. Now, one thing that you have to keep in mind when you're calculating the covariance is that in contrast to the variance, this value is not necessarily positive or equal to, it could be equal to 0, but it's not necessarily positive. So you could have, for example, let's say the number of bedrooms again, and let's come up with another variable. We're going to call this c, which is going to be the number of people that bid for the house. Let's say this is an auction and people can bid on it, can say that they're going to pay for it, something like that. So you would expect, this is a gross sum and simplification. Obviously, you wouldn't see this in real life, but you would expect that the more bedrooms a house has, the more expensive it's going to be. And consequently, the less people are going to be able to bid for that house because it's going to be so expensive that it doesn't make any sense for a lot of people to just bid for it. Or on contrast, maybe it's somebody with a small family wouldn't need such a big house. It's just going to be too expensive for them. So in this kind of case, we would expect to see that the covariance between these values is going to be less than 0. So this is just to drill down the idea that the covariance need not be positive. So the covariance matrix is just simply a way to organize this information in a matrix form. And the shape that this thing has is, let's say we have n variables. So this is going to be an n by n matrix where each element in the diagonal is going to be equal to the variance of that variable, in this case column. And each of the other elements is going to correspond to the covariance of those two elements. And there's different notations on this, but what this means is the covariance between variable 1 and variable 2. And you will have that so on and so forth until covariance of 1 with n, and then you're going to have the same here. Now, one good thing about this matrix is that this term, covariance of n with 1, is the same as this term, covariance of 1 with n. That is to say that the matrix is symmetrical. And that's going to come in handy whenever we're doing a lot of operations with this kind of thing. So in summary, the covariance matrix is just a way to organize the information and to have it here. And now that we understand what the expected value represents, what the variance represents, and what the covariance represents, we are able to code up our matrix by using this expression and the expression for variance that we talked about earlier on. Okay, so now that we understand the covariance matrix, let's dive into the code. I'm going to follow the official solution from DeepML. I tried to do something on my own, but it was a bit messier than this one, and I think it's pretty good. So let's roll with it. So what we're going to do, this is just for a quality of living improvement. We're going to first define the dimension variables, which is going to be the number of features and the number of observations. So how many rows our data set has and how many columns it has. And so it's going to come from this. So these vectors is going to be a list of lists, and each entry is going to be the observations for each of the different columns. Then we're going to initialize our return, which is going to be the covariance matrix. And the way we're going to do this is we're going to say, in Python, you can do this multiple different ways. I prefer to do it with a list comprehension. So what we're going to say is for something in range number of features. If you're not familiar with what this means, this is basically saying to Python, hey, don't worry about what the name of the variable within the for loop is going to be. Just run the for loop. That's all we care about. And we're going to do this in order to generate an n by n matrix. So a matrix that is going to be of dimension number of features times number of features, as we saw on the example that we talked about. And finally, just to make our lives easier, what we're going to do is we're going to pre-calculate the means. Remember that all of the formulas for the variance and the covariance has an expected value. And so the way we approximate the expected value in a sample is by using means. So we're going to say means is going to be equal to the sum of whichever feature we're looking at over the number of observations. So you're going to sum all of the elements in the column and divide it by the number of rows that you're looking at. And so this is going to be for a feature in the vectors. And then what we're going to do is we're going to populate the return matrix. And let me just write the return statement here. So there's a lot of different ways you can do this. I'm going to just follow the nomenclature from the official solution. So for I in range number of features, for J in range number of features. So this can be like rows for I and columns for J. What we're going to do is we're going to pre-calculate the value. So we're going to pre-calculate this covariance. And then what we're going to do is we're going to assign at this position in the covariance matrix the value that we have just pre-computed. And I know that the official solution does this line a little bit different, but I think this is going to be a bit more clear. Because the matrix is symmetrical, we can do it. We have to update ij, that is at row I, column j, and at row j, column I, because it's the same value. And you could do this to speed up the for loop. It's not necessary for you to iterate over all combinations of rows and columns, but because the test cases are so small, it doesn't really matter. So with that said, let's calculate this value. So what we're going to do is we're going to calculate a sum. So this is kind of like taking an average, right? Because if we go back to what we wrote here for the covariance, this is going to be the expected value of this mess that we have right here. And we know that to approximate the expected value, we have to take a mean. Now, the thing that's going to be slightly different here is that instead of dividing by the number of rows, we're going to divide by the number of rows minus 1. If you're wondering where that's coming from, this is a term to reduce the bias of our estimator. This comes from a lot of econometrics classes and statistics classes. I'm not going to go deep into that because it kind of takes a little bit, at least when you're doing that for the first time. But rest assured that that's kind of the quote unquote trick. This is just to prevent a bias in our estimation. So with that being said, let's calculate this value. So what we're going to do is we're going to graph the values at a specific column, which we're going to call column K. And we're going to subtract that from the means of the elements at column I. So what basically this is saying is that, hey, look at the means for one of the specific columns here in our data set, and we're going to subtract that from all of the terms that of the sum of all of the difference of all of the terms minus that means that we have there. And we're going to do something similar for the elements in the other column, which is J. And so once we do all of that, you'll notice that we came up with a variable named K. So what this K is going to be a way for us to iterate over all of the observations in the data set. And so basically, this is just going to be the way in which we calculate the values for the covariance matrix in our sample. And with that done, the only thing that's left for us is to return this value. So we're going to run it. We're going to wait a little bit, and we should pass all of the test cases without any problem. And there you go. We passed both of the test cases. And so we know that this solution works. Okay, so we talked about how to do it from scratch. Let's talk about how you will do it more likely than not during your whole life using Numpy. So first of all, we're going to import Numpy, and then Numpy has this very handy command called cov, which is going to calculate the covariance of our element. So the only thing we should keep in mind, and I'm not entirely sure if this is strict or not, but I would assume it is that instead of just passing vectors as a list of lists, we would pass vectors as a Numpy array. And if we run this one-liner, this should also pass all of the test cases. And there you go. This also works. So code it out from scratch at least once so you get an idea of how it works. But in real life, you're going to use Numpy all of the time. Thank you so much for watching. I hope this video was helpful. If you have any questions or comments, please leave it in the comments below. And I hope to see you soon.